Today we want to talk about an important application of the Lagrangian formalism. In this case, we want to introduce the idea that we can generate a Lagrangian for every second-order ordinary differential equation. In this case, we are speaking in the context of classical mechanics, where the physical system that we are dealing with is described by the generalized coordinates q and maybe p for the Hamiltonian. In this case, we are going to deal with a Lagrangian that depends on q, q dot, and t. Okay, and when we are going to show that for a given second-order ordinary differential equation, we can find this Lagrangian, and while using the Euler-Lagrange equations, well, we can find with this Lagrangian we can get that differential equation. So to do this, we are going to start by introducing an example, a very famous example known as the Damped Harmonic Oscillator. That example, well, we are going to explain it with a spring that is joined with a block of mass m, and this spring has a coefficient k of restitution. Okay, let's say, for example, that we are going to establish the reference system here. Well, in that case, actually, it will be here. Okay, just to make it easier. Here we have the x equals 0, and to the other side, well, it will be the negative x values. Okay, so we want to notice here that due to the air resistance, we are going to have also a damping force. Okay, that damping force will be always opposite to the motion of the block. Okay, so for example, if the block is moving to the right, then the damping force is going to be pointing to the left. Okay, and if the block is moving to the left, well, the damping force will be pointing to the right. Okay, that is because there is an air resistance. In this case, well, we could have other examples where the damping force is generated by other reasons. Okay, so in this case we have the damping force. We are going to name it as F gamma. Okay, and also, for example, if the block is moving through the right, okay, well, the force of the spring acting on the block will be pointing to the other side. Okay, to the left. But for example, if the block is moving through the negative x values, okay, the spring will be in compression. So that means that the force of the spring will be applied to the right. Okay, that is if the block is moving to the left. Okay, so it's opposite to the values of x. We can establish that with the next equation. We are going to say that fk is going to be negative kx. Okay, so if x is positive, then this force is negative, but if x is negative, this force is positive. And remember that when x is negative, that means that the spring is in compression. And we are going to define the damping force as negative 2m gamma x dot. In this case, again, it's something similar. The damping force is opposite to the velocity of the block of mass m. And remember that the velocity is always pointing on the direction of motion. So using the Newton's second law, we can establish a differential equation for this example. We know that, well, the total force of the block is going to be m times x dot dot, where this is the acceleration of the block, and this is going to be equal to the sum of every force acting on the block. That is the spring force minus kx and then minus 2m gamma x dot, the damping force. Okay, we also know that on the study of harmonic oscillators that K can be defined as m omega squared. This is a very famous formula, so if we substitute, we are going to get minus m omega squared x minus 2m gamma x dot. And if we cancel the m's, well, we are going to get that x dot dot is equal to plus 2 gamma x dot plus omega squared x is equal to 0. And in this case, we can identify the generalized coordinate x, and we are going to name it q. Okay, so an equivalent differential equation will be q dot dot plus 2 gamma q dot plus omega squared q equals to 0. Okay, so what I want to do with this equation to explain the concept of this video is that we can establish that q dot dot is equal to negative 2 gamma q dot minus omega squared q, because this can be seen as a function f that depends on q dot, q, and maybe t. In this case, well, we do not have any t explicitly on the expression, but in general, we can have other examples that have the t. So this process is going to apply for functions f that depends on q dot, q, and t. Okay? Okay? So after saying this, well, we are going to study the Lagrange equations applied to this general Lagrangian that we have mentioned that depends on q, q dot, and t. What happens if we calculate the Euler-Lagrange equation on this Lagrangian? For example, we are going to calculate first the derivative of the Lagrangian with respect to q dot. If we calculate this, we can see easily that this will be another function that also depends on q, q dot, and t. Okay, this also depends on these three variables. So the Lagrange equations tell us that we need to calculate then the derivative with respect to time of this quantity. So we can do that. The derivative with respect to time of the partial of L with respect to q dot. And what will that be? Well, looking that we have these three variables here, we need to use the chain rule to establish the next. This will be the partial with respect to q of the partial of L with respect to q dot, okay, times q dot, okay, because this is like the derivative of q with respect to time using the chain rule, but we are going to name it as q dot, and then plus the partial with respect to q dot of the partial of L with respect to q dot times q dot dot, and then plus the partial with respect to time of the partial of L with respect to q dot. Okay, well, we can rewrite this as the second partial of L with respect to q and q dot times q dot plus the second partial derivative of L with respect to q dot dot plus the second partial of L with respect to t and with respect to q dot. Okay, and remember that on the Euler-Lagrange equation we also need to calculate dl with respect to q, so that, well, it remains the same. Okay, we cannot do anything to this. Okay, so just establishing the Lagrange equation, we are going to get this, and then minus the partial of L with respect to q, and this will be equal to 0. Okay, another thing that we need to mention is that we have something known as the Clairaut theorem, that it says that, well, if we have two continuous and existence of the second partial derivatives of a function of two variables, for example, let's say f of x comma y, if the first and second partial derivative with respect to x and with respect to y are continuous and they exist, well, we can switch the order of the derivatives. For example, that means that the second partial of f with respect to x with respect to y, it will be equal to the second partial of f with respect to y with respect to x. Okay, we can switch the order of the derivatives. This is because of the Clairaut theorem. Okay, so we are going to do something like that in this process. Okay, but first of all, let's notice that we have a q dot dot here, and we said that q dot dot can be defined as a function of q dot, q, and t, okay, due to the existence of this differential equation. Every example that where we can apply this process needs to be of a differential equation of this form, okay? So that means that we can find this function f. And that also means that we can rename this q dot with f. Okay, so we are going to get the next. Okay, we get that equation. Well, we are going to take the partial derivative with respect to q dot in every part of this equation, okay? Okay, so it will be something like this. We need to take the derivative on every term. Okay, so looking at, for example, here we have a product of functions. We need to use the product rule. So what are we going to get? Well, if we do this here, well, first of all, let's take the derivative of this times this. Okay, so that will be just this. Okay, so this is the derivative of this is 1, and the derivative and times this. Okay, and then plus, we will see this as the next, the derivative with respect to q of the second partial of L with respect to q dot, okay, because we are taking the derivative here and we are switching the derivatives. Look here that we will have a third derivative, first with respect to q dot, then with respect to q, and then with respect to q dot, but we are changing the order of the derivatives to take the partial derivative with respect to q to the last. So if we do that, we take two partial derivatives with respect to q dot first, and then the partial derivative with respect to q. And this multiplies q dot. Okay, now we go with the second term. We are going to remain this as the partial with respect to q dot of the second partial of L with respect to q dot squared. Yeah, taking the derivative of the first term times the second times f, and then plus the partial of f with respect to q dot, and then times the first term, which is the second partial of L with respect to q dot squared. Okay? Okay, and then, well, we are going to take the derivative with respect to q dot of this term over here. So that will be plus the partial with respect to time of the second partial of L with respect to q dot squared. Again, switching the order of the derivatives. Look that we are actually trying to leave the second partial of L with respect to q dot because we are going to introduce a new variable there. Okay, you're about to see it, and then minus the partial with respect to q dot with respect to q of L, and this will be equal to 0. Okay, and this will be the second partial derivative. What you can notice here is that this term can cancel with this term just by switching the order of the derivatives again. Okay, and we are going to introduce, like I said, a new variable m that will be defined as the second partial of L with respect to q dot. Okay, if we do that, then we can establish a new differential equation that will be the partial with respect to q of m times q dot here plus f times the partial with respect to q dot of m, and then plus the partial of f with respect to q dot of m, and then plus the partial with respect to time of m equals to 0. Okay, so we can rewrite this equation as q dot, the partial with respect to q of m, and then plus, looking at f is q dot dot, we are going to rewrite it again, times the partial with respect to q dot of m, plus the partial with respect to time of m. This will be equal to negative the partial of f with respect to q dot m. And look, if we inspectionate this expression that we have here, we can immediately see that it is actually the derivative with respect to time of m, the total derivative, okay? Where m is a function of q, q dot, and t. If m is a function of these three variables, and if we take the total derivative with respect to time, we are going to get this, again using the chain rule, and well, yeah, noticing that q, q dot are functions of t. Okay, so that means that we can establish that the total derivative with respect to time of m is equal to negative the partial of f with respect to q dot m. Okay, so that will be like another way to simplify the process. Okay, and remember that we defined m to be the second partial of L with respect to q dot. Okay, this will be also necessary then to be able to find the Lagrangian. Okay, and if we remember, f was defined to be minus 2 gamma q dot minus omega squared q, in this case for the example of the damped harmonic oscillator. Okay, so we write that f is equal to minus 2 gamma q dot minus omega squared q. Okay, so if we work with this expression, for example, let's calculate the derivative of f with respect to q dot, as this equation says. So that is the partial of f with respect to q dot is equal to, well, minus 2 gamma. So for the damped harmonic oscillator, we get that the total derivative with respect to time of m is equal to, well, negative this quantity, so that will be 2 gamma m. Okay, so in this case we have a very easy differential equation that is like immediately solved. We can see easily that a solution for that differential equation is m equals m e to the 2 gamma t. And an important fact to notice here is that when we take gamma, the damping constant, equal to 0, well, we can recover the harmonic oscillator without any damping force. Okay, perfect. So looking that we already found m, and we know that m was defined as the second partial of L with respect to q dot, well, this means that m e to the 2 gamma t is equal to the second partial of L with respect to q dot squared. Okay, so remember that the main goal of this process was to find a Lagrangian corresponding to a differential equation. So we need to solve now this differential equation to find that Lagrangian that we need. Okay, but look that this expression does not depend on q dot. Okay, so this can be seen as the partial of L with respect to q dot, and then the partial of this quantity with respect to q dot. Okay, so that means that the partial of L with respect to q dot, it will be just the integral of m e to the 2 gamma t dq dot. Okay, and that means that we will have, for example, m e to the 2 gamma t times q dot, and then, well, in a regular integral we will have a constant here, but not in this case. In this case, looking that the integral is with respect to q dot, and we are dealing with functions of q dot, q, and t, well, the remaining will be a function that will be only depending on q and t. Okay, that means that, well, the partial of this quantity with respect to q dot, okay, well, it will be m e to the 2 gamma t, because the partial with respect to q dot of this is 0. So that this is like our constant of integration. Okay, and we can do the same process again to find L. This L will be the integral of m e to the 2 gamma t q dot plus h of q comma t with respect to q dot. Okay, so if we solve this integral, we will get that this is m e to the 2 gamma t q dot squared over 2 plus h q dot plus g of q comma t, again as a constant of integration. So, okay, this will be the Lagrangian that we need. Okay, but what happens with h and g? We do not know what are the expressions that describe these functions, but what we do know is that, well, the Lagrangian needs to satisfy this equation over here. So let me copy this equation because we are going to use it again. Okay, so we now need to substitute the Lagrangian on that equation. Look that we are going to use in these three terms the partial of L with respect to q dot. So let's begin with that. Let me calculate the partial of L with respect to q dot. That is very easy to notice that that will be m over 2 e to the 2 gamma t q dot times, well, 2, that will cancel with this 2 over here, and then plus h. Okay, perfect. So now, first we have here the partial with respect to q of that thing that we just calculate here, the partial of L with respect to q dot. So the partial with respect to q of the partial of L with respect to q dot will be just the partial of h with respect to q. Looking that this term does not depend explicitly on q, the partial of L with respect to q, well, sorry, the partial of this with respect to q will be just 0. And then looking that h is a function of q, we just express this as the partial of h with respect to q. Okay, now this term says that we need to take the derivative again with respect to q dot. So the derivative with respect to q dot of the partial of L with respect to q dot, it will be, well, m e to the 2 gamma t. Okay, perfect, because h does not depend on q dot. Now we need to calculate the partial with respect to time of the partial of L with respect to q dot. Okay, so what will that be? It will be, well, m q dot 2 gamma e to the 2 gamma t plus the partial of h with respect to time. Okay, in this case, q dot is considered as a constant. So this will be equal to 2m q dot gamma e to the 2 gamma t plus the partial of h with respect to time. And then finally we are going to calculate the partial of L with respect to q. Okay, so if L is this, well, okay, it will be q dot, the partial of h with respect to q, plus the partial of g with respect to q. Okay, looking that in the Lagrangian, only h and g depend on q. Perfect. So now we just calculated every term of the equation. So if we substitute for the first term, this term, well, we are going to get q dot, the partial of h with respect to q, and then plus q dot dot times this quantity over here, the second partial of L with respect to q dot, which is m e to the 2 gamma t, plus it will be this one over here, which is 2m q dot gamma e to the 2 gamma t, plus the partial of h with respect to time, okay, and then minus the partial of L with respect to q, and that is q dot the partial of h with respect to q minus dg dq equals to 0. Okay, so we have that equation over there. We see here that we can cancel this term with this term, and we know that q dot was defined to be minus 2 gamma q dot minus omega squared q. So we are going to plug this into here, and we get that minus 2 gamma q dot minus omega squared q m e to the 2 gamma t plus 2m q dot gamma e to the 2 gamma t plus dh dt minus dg dq is equal to 0. Okay, look here that this term multiplied by this term and this term can be cancelled, okay, because they are actually the same. We have minus 2 gamma q dot m and then plus 2m q dot gamma and then e to the 2 gamma t on both terms. So this cancels with this, and we are going to get that minus omega squared q m e to the 2 omega t plus dh dt minus dg dq is equal to 0. And notice that, well, we are going to use a trick here. We are going to say that the partial of h with respect to t, then minus the partial with respect to q of g, and then look, plus omega squared q squared over 2m e to the 2 omega t will be equal to 0. Okay, if we take the partial of this quantity with respect to q, well, we will get this expression that we have here. So this is just to group this term as a function that is being derived with respect to q. Okay, so look that we have two functions that are being partial differentiated and they are equal to 0. So first of all, we can rewrite this as the partial of h with respect to t, that is equal to the partial with respect to q of g plus omega squared q squared m e to the 2 gamma t over 2. And this implies that there exists a function f that depends on q and t, such that the partial of f with respect to q is equal to h, and the partial of f with respect to t is equal to g plus omega squared q squared m e to the 2 gamma t over 2. Okay, so in terms of that function f, we can define g equals the partial of f with respect to t minus omega squared q squared m e to the 2 gamma t over 2, and h is equal to, well, the partial of f with respect to q. Remember that these are the expressions, well, the functions that we didn't know on the definition of the Lagrangian that we found, okay? We found this Lagrangian for that differential equation, but we found two unknown functions, h and g, that we wanted to find. So that means that we can write those functions h and g in terms of the function f, Okay, so the Lagrangian is this, but we just found that this will be h as the partial of f with respect to q, and then plus g, where g is the partial of f with respect to time, minus omega squared q squared m e to the 2 gamma t over 2. Okay, and look that, well, just to make things simpler, we have a common factor here, m e to the 2 gamma t over 2 here and here. So we can establish that the Lagrangian is m e to the 2 gamma t over 2 times q dot squared minus omega squared q squared. Okay, and then plus q dot the partial of f with respect to q plus the partial of f with respect to time. Okay, perfect. So this will be like a general result. Okay, for the damped harmonic oscillator, this will be like a general Lagrangian. But looking that f is kind of an arbitrary function, we can also establish that f could be equal to 0, making that, well, a particular Lagrangian for the damped harmonic oscillator will be only m e to the 2 gamma t over 2 times q dot squared minus omega squared q squared. Okay, in that case, we can have some other functions f that are not 0 that will be also part of the Lagrangians that correspond to the second order ordinary differential equation of the damped harmonic oscillator. But in this case, this will be like a particular case, okay? But it's also valid. So this will be just the final important result of the video. And if you have any question about this process, you can leave it on the comments.